Hello, I'm Jeff Beer, founder of the Embedded Vision Alliance and president of BDTI. I'm here today on the campus of the University of California at Berkeley with Professor Jitendra Malik. Professor Malik has been on the faculty of electrical engineering and computer science here at UC Berkeley for 25 years and has had a huge impact on the field of computer vision, both through his teaching and research over that time. Professor Malik, thank you very much for taking the time to speak with me this morning.
Thank you, Jeff. I'm happy to be here.
You started working in computer vision 30 years ago when most people hadn't even heard of the field. Now it's beginning to increasingly come into the awareness of everyday consumers in products like video games and automotive safety systems and so on. When you started 30 years ago in computer vision, what were your expectations about how the field would evolve?
At that time, computing power was really much less compared to what we have now. So, in some sense, we were really crazy to be trying to work on in this field at that time, because normally people talk. The way I'd like to think about it is the following. Normally, we talk about Moore's law in the forward direction. So you say every 5 years, computing becomes 10 times faster, or memory increases, storage increases, etc., etc. To get a sense of how things were in the 80s when I started, you have to run Moore's law backwards. So you have to imagine that, okay, 20 years back, computers were 10,000 times slower, or storage was 10,000 times less, or whatever. And that was the scenario in which we started to work in this field. And I'm, of course, not the first generation of people in the field. In a sense, there was work in the 60s and 70s as well. I got into the field in the 80s. So at that time, the field was essentially driven by a pure curiosity-driven scientific agenda. We knew that humans can see. I mean, humans somehow managed to make sense of the world in which we live, starting from single photographs or a video stream. So therefore, we know it must be possible. So it's like if you were in the late 1800s and you saw birds fly, then you knew it must be possible somehow for some heavier than air object to fly. But we didn't have airplanes at that time. But you had the sense that it should be possible. So that's what I think we were in, the state we were in the 70s or 80s, which is that we knew it should be possible, and humans somehow do it, and so we were just trying to figure out how. And what we did was we started to formulate the problems, and in a certain sense, all the basic problems that we work on today, we had formulated them back in that era. We didn't have very good solutions, but we had got a sense of what were the important aspects of the problem. And then we would construct mathematical models and algorithms. And those mathematical models and algorithms would be very simplified, because we were constrained by what we could implement and try out on the machines of the time. And that necessarily was quite a bit less than what we can do today. And but there was significant advance in terms of mathematical modeling and basic algorithms. Then, as technology got better, as computing power was more and more available, and computers were faster, we had more storage, what we could do was to evolve our algorithms and thinking, so that certain ideas which we had but we couldn't really dare to explore experimentally, we could start to explore. Mm-hmm. And that really happened in the 90s. So I would say the first successes of computer vision start off in the 90s. I mean, I would say they're in two strands. One strand is the strand to do with geometric reconstruction, where some of the first successful applications were developed in the 90s, and they had an impact on the movie industry in visual effects and eventually in video games. The other pathway was the one of trying to make sense of images and video, which means recognizing objects in images and video, And the big success there was face detection, which today, of course, is there in every camera. But the algorithms which showed that it could be done were developed in the late 90s. I should mention that there were applications of image recognition before that in the field of OCR, optical character recognition and digit recognition. In the 90s, there were successful systems developed which could do, for example, handwritten digit recognition for the purpose of reading the amount on a check, for example. So I would say those are successes which predate face detection probably, but that seemed like a very narrow specialized application. And face detection is something which everybody gets, right? Everybody is going to have a camera, but not everybody needs a machine which reads checks. Only a bank ATM needs to have that capability, right? So entering the consumer market really happened with the ability to detect faces, because that ability got put into every camera.
So what are some of the key topics of your current research projects?
So currently I'm focusing almost exclusively on the problem of recognition, and this is the problem that we start out with an image. It's just a collection of pixels, and we sort of want to uncover the semantics inside. We want to know what are the objects in the image, what are the people in the image, where are they, what are they doing. In a way, what we want to be able to do in the grand goal is start with a photograph and be able to convert it to like a paragraph of English text which describes what's happening in this image. We should be able to say, in this image, so like the scene right now, we should be able to describe this as there are two people sitting on chairs talking to each other, and behind them is a whiteboard, and we should be able to say this from an image.
Maybe I've got the wrong impression, but it's my impression that this kind of problem has been at the heart of computer vision research for decades.
Yeah.
Why is that? Why isn't it a solved problem already? It's just a really hard problem.
Yes. In fact, I would say it's been around for 50 years or 60 years, depending on how you want to count. The first PhD thesis in computer vision is supposed to be Larry Roberts' PhD thesis, which was, I think, in 1963. And he actually addressed the problem of object recognition. For him, the objects were a cube and a prism, okay, two wooden blocks. I mean, there was like, he had the choice of, in the image there would be one of three possible objects, a cube or a prism, and he had, the goal of his program was to say which one it was. Right. So, but it was, computer vision started out as a subfield of artificial intelligence, and from that perspective, the grand goal was, okay, can we get computers to do what humans can do? So the grand objective was set back then. I think we went through early phases where people had a very naive view of what it would take to solve the problem, and so there would be fairly simple-minded approaches, and people would think, okay, maybe this will work, and maybe in 5 years it will work. Okay, and those really failed. And I think that it's only starting in the 90s that I would say the work on the problem became really serious, in the sense that people stopped making claims that we are going to solve this in 5 years or whatever. It's worth keeping in mind how difficult the problem is. So I think it's something like 30 to 50% of the brain, the human brain, is devoted to visual processing. So now we can, so this is, and the human brain is a remarkable instrument. It's a result of billions of years of evolution. The computing power associated with this 30% of the brain is quite significant. I mean, we have on the order of 100 billion neurons in the brain, and each of these neurons may be connected to 10,000 other neurons. And if we think that the computing power resides in the synapses, then we are talking of 10 to the power 15. 10 to the power 15 units. Okay, now let's think about where computers are today, right? So now we can have devices which have 10 to the 9 units quite readily. But and these devices, transistors are faster than neurons.
Mm-hmm.
So essentially we get a little gain from that when designing artificial systems. But now, or say, if we put, say, 1,000 of today's machines together, or maybe in 5 years from now, we are now approaching the kind of computing power we need, right? But 20 years ago, we were simply off by orders of magnitude.
Mm-hmm.
So I think that even if we had all the right ideas, we didn't really have a way to realize them.
Mm-hmm.
And what happened actually was that we, in fact, filtered out the right ideas because we were always constrained by what you can experiment with. And when your experimental apparatus doesn't let you do the right thing, you will go down some pathway where you try to do the wrong thing.